Hello everyone and welcome to Mathematics and Control Engineering tutorials. In this tutorial we explain how to compute the eigenvalues and eigenvectors of a 2 by 2 matrix. In particular, let's solve this example over here. To be able to solve this problem, we first need to recall the definition of the eigenvalue and eigenvectors. Namely, let lambda be an eigenvalue. I will write it over here, eigenvalue. And let W be the corresponding eigenvector. If lambda and W are eigenvalue and eigenvector, they satisfy this equation. A multiplying the eigenvector should be equal to lambda multiplying eigenvector. Over here, lambda can be a complex number. Let us, just for simplicity, assume that lambda is just a scalar. Then, what's the meaning of this equation? Well, if we multiply A by eigenvector, we will actually obtain the eigenvector that's either scaled or that's scaled and whose direction is being reversed for 180 degrees. That is, the action line of W and lambda times W are the same. Okay, so now that we know that and that we recall the definition of the eigenvalue and the eigenvector, we can proceed. From this equation, we obtain that A multiplying W minus lambda multiplying W is equal to 0. Over here, we have that A multiplying W minus lambda, and instead of W, I can write lambda multiplying identity matrix multiplying W is equal to 0. Over here, the identity matrix is a matrix that looks like this. 1, 0, 0, 1. Okay, now from this equation, I have that A minus lambda I multiplying W is equal to 0. For the time being, let us assume that lambda is a known number. Then, this is a matrix, that is A minus lambda I is a matrix with known coefficients, and we have a matrix multiplying the unknown vector W, and this is equal to 0. This is actually a homogeneous system of linear equations where the unknowns are the entries of W. Okay, now the main question is, when does this system have non-trivial solution? I will write it here. What is a non-trivial solution? So what is a non-trivial solution? The non-trivial solution is a solution W whose at least one entry is not equal to 0. For example, W can be 0, 1, 1, 0, or any number instead of 1 over here, or it can be fully populated. For example, 1.5, 1.6. So these are the non-trivial solutions. That is, over here, we have that W has at least a single non-zero entry. On the other hand, trivial solution is W is equal to 0, 0. This system always has a trivial solution. That is, it always has this type of solution. However, we want to ask ourselves, when does the system have non-trivial solution? The main condition for the existence of the non-trivial solution W is that the determinant of this matrix is equal to 0. That is, the condition for the existence of the non-trivial solution W is that the determinant of A minus lambda I is equal to 0. This equation is called characteristic equation. Then, if we compute this determinant as a function of lambda, we will obtain a polynomial that depends on lambda. That is, a polynomial whose independent variable is lambda. And over here, I will write this polynomial. P of lambda, meaning that the polynomial depends on lambda, is equal to the determinant of a minus lambda I. And this polynomial is called the characteristic polynomial. To summarize, eigenvalues are zeros of the characteristic polynomial. That is, eigenvalues lambda solve this equation. Okay, once we compute the eigenvalues by solving this equation, that is, by computing the zeros of the characteristic polynomial, we can compute the eigenvectors as non-trivial solutions of this system equations where the unknown, or better to say unknowns as plural, are the entries of the vector W. And over here it's assumed that the eigenvalue is fixed and known. That is, for every eigenvalue we will have to solve the corresponding system of equations to compute W. Okay, let's proceed with the example. Our goal is to compute the eigenvalues and eigenvectors of this matrix. The first step is to find the eigenvalues. So let's write this thing. We want to find the eigenvalues. How do we find the eigenvalues? First of all, we need to compute the characteristic polynomial, and then we need to find the zeros of the characteristic polynomial. In our case, the characteristic polynomial is a determinant of a minus lambda I. And we set the characteristic polynomial to 0. So let's compute a minus lambda I. We have a is 7 minus 4, 5 minus 2. Okay. Lambda is a complex number multiplying the identity matrix 1, 0, 0, 1. Okay. Let's proceed. This is equal to our A matrix, 7 minus 4, 5 minus 2. And over here we have lambda is a complex number, and if you multiply lambda by the identity matrix, we obtain lambda 0, 0 lambda. That is, multiplication of a complex number and a matrix is performed element-wise. That is, lambda multiplies this entry, lambda multiplies this entry, lambda multiplies this entry, and lambda multiplies this entry. And now we have to just compute the resulting matrix. We have 7 minus lambda over here, then we have minus 4, then we will have 5 over here, and then we will have minus 2 minus lambda. And here is our final matrix. The next step, we need to compute the determinant of this matrix. So let's do that. The determinant is 7 minus lambda multiplying minus 2 minus lambda. And then we have minus 1 multiplying minus 4 multiplying 5 becomes plus 20. Let's nicely write this. So this is the determinant. Let's multiply all the entries together. We have minus 14. Then we have minus 7 lambda. Then we have plus 2 lambda. And finally we have plus lambda squared. And this becomes lambda squared. Then we have minus, of course I forgot here, let's not go too fast, plus 20, okay? And then this becomes lambda squared, Then we have minus 5 lambda, and over here we will have 20 minus 14 actually becomes, let's see, plus 6. Okay, now to compute the eigenvalues, we need to compute the zeros of this quadratic polynomial. Lambda squared minus 5 lambda plus 6 is equal to 0. The zeros are lambda 1, 2 is equal to. Here we apply the standard equation for computing the zeros of quadratic equation. We have 5 plus minus square root of b squared, it's 25, minus 4ac, minus 4 multiplying 6 divided by 2. And finally this becomes 5 plus minus 1 divided by 2. We see that lambda 1, that is the first eigenvalue, is equal to 5 plus 1 divided by 3, that's 6 divided by 3, that's 3. And the second eigenvalue becomes lambda 2 is equal to 5 minus 1 divided by 2, that's 4 divided by 2, that's 2. Let's nicely write it 2. Okay, so here are the two eigenvalues, 3 and 2. The next step is to find the two eigenvectors. Okay, for every eigenvalue that are repeated over here, we will have the corresponding eigenvector. So let's start for lambda 1 is equal to 3. For this lambda, we need to form the corresponding system. That is, we need to form the system a minus lambda 1 multiplying I and multiplying the corresponding w. And this should be equal to 0. We need to solve for w. However, let's first form the matrix a minus lambda 1 I. So a minus lambda 1 I becomes, let's write, we have a over here, 7 minus 4, 5 minus 2, minus lambda 1, 1, 0, 0, 1. Then we have further 7 minus 4, 5 minus 2, and lambda 1 is obviously 3, so we have minus 3 multiplying 1, 0, 0, 1, and we further have 7 minus 4, 5 minus 2, and over here we will have minus 3, 0, 0, 3. And finally we have a minus lambda 1 I is actually, let's see, 7 minus 3 becomes 4. So we have 4, then we have minus 4, then over here we have 5, and we have minus 2, minus 3, minus 5. Okay, so this is our matrix. What's the next step? Next we need to form the system. So after substituting this matrix inside of this system, we will have, and I will write it over here, 4 minus 4, 5 minus 5, multiplying, then instead of w, we can write w1, w2, where w1 and w2 are the entries of w. Let's write it down over here. W is actually w1 and w2. And then what do we have over here? We have 4w1 minus 4w2 is 0. And then we have that 5w1 minus 5w2 is also equal to 0. So what is the solution of these two equations? Well, let's analyze these two equations. Now, if we divide the first equation by 4, we will obtain w1 minus w2 is 0. So this is the first equation. On the other hand, if we divide the second equation by 5, we will obtain that w1 minus w2 is equal to 0. So it looks like that these two equations are equivalent to each other. That is, they're linearly dependent. Or better to say, these two equations are linearly dependent. And this is expected since the corresponding determinant a minus lambda 1I is actually equal to 0, which means that that determinant has two linearly dependent, or better to say, yes, linearly dependent rows or columns. So instead of these two equations, we only have a single equation. And this single equation is that w1 is equal to w2. Or let's write it first in the general form. It's w1 minus w2 is equal to 0. And from here we have that w1 is actually equal to w2. Okay, so what did we obtain over here? We obtained that w1 is actually equal to w2. And w2 can be anything over here. So you can pick any number you wish for w2, and w1 will simply be equal to w2. That is, w2 over here is free variable. Free variable means that you can choose it freely. This means that in reality, we actually have an infinite number of eigenvectors for this eigenvalues. However, these eigenvectors are actually parametrized, and let's write them like this. W, that is, our eigenvector, is some parameter, beta, that we can freely choose, multiplying 1, 1. Why this is the case? Well, if we multiply this, we obtain beta, beta. Okay, now if you see from here, w2 is free, and w2 serves as beta. So here, instead of beta, you can think of w2, which we can freely choose. And then, according to this equation, w1 is equal to w2, that is, w1 is equal to beta. And that's precisely what is written over here, where beta is any real number. So from here we see that we have an infinite number of eigenvectors. They're actually represented by this vector that's simply scaled. That is, this is a vector that makes 45 degrees with the horizontal axis, and that can be simply shifted along that action line, and that's it. Next, let's find the eigenvector for lambda 2 is equal to 2. So we have A minus lambda 2 multiplying the identity matrix is, let's now quickly substitute the values since we already know the main ideas and we know how to multiply things. So we have 7 minus 4, 5 minus 2, minus, what is lambda 2? It's equal to 2, and 2 multiplying the identity matrix becomes 2, 0, 0, 2. And this further becomes 7 minus 2 is 5. Then we have here minus 4. Then we have 5 over here. And over here we have minus 4. Okay, so our system now looks like this. A minus lambda 2 multiplying I multiplying W is equal to 0. So the system becomes 5 minus 4, 5 minus 4 multiplying W1, W2 is equal to 0, 0. And if we expand this system, we will obtain. Let's write it over here. The first equation is 5 multiplying W1 minus 4 W2 is equal to 0, and the second equation is 5 multiplying W1 minus 4 multiplying W2 is equal to 0. Again, we see that these two equations are actually equivalent, or better to say identical. Consequently, we have only a single equation. That equation is 5 multiplying w1 minus 4w2 is equal to 0. And from this equation, we actually obtain that w1 is equal to 4 over 5 w2, where w2 is free variable. Okay, this is very important. Again, all this means that we have an infinite number of eigenvectors for lambda 2 is equal to 2. We can simply select any real number for w2, and w1 is simply computed like this, and this is our eigenvector. Consequently, the eigenvector can be parameterized like this. Over here, I will use alpha, and alpha will play the role of w2, that is of our free variable, and we will have 1 over here, that is, the last entry is 1, and the first entry is simply 4 over 5. And that's it. How do we know that this is correct? Well, if we multiply this, we will have 4 over 5 multiplying alpha, and over here we will have alpha. Alpha plays the role of w2, and w1 is equal 4 over 5 multiplying alpha. Okay, that's all for today.